Subscribe now.
Hello my dear children, this is going to be a very small yet very important video regarding acidic strength. There are many questions in the competitive exam and children often get confused about the strength of an acid. So today I am going to make this basic video which will clearly clear all your doubts about the acidic strength. My name is 𝐕𝗵𝗲𝗏 and you are watching 𝐕𝗵𝗲 classes. So we all know that any substance, according to Arrhenius, any substance which when dissolved in water, any substance when dissolved in water, it gives you H plus ion or H3O plus ion, then it is an acid. This is a basic definition for an acid. Though we don't follow this definition today, we follow Lewis definition, but this is one of the basic definition for an acid. That means if I take an acid HA and it is dissolved in water, understand that HA is a general expression or general formula of an acid. It dissolved in water, it is giving you H plus ion and A minus ion. Then we call this substance as an acid. This everybody knows, right? And we say that how easily it is giving you H plus ion, that decides the acid strength. But that is not exactly true. It is the conjugate base of this acid is how stable, how much stable. We all know that HA, if HA is the acid, A minus would be the conjugate base. So the more stable the conjugate base is, the more acidic the acid will be. Here basically it doesn't depend, the strength of an acid doesn't depend on how easily it is leaving H plus ion, but it depends on the actual reason is more stable the conjugate base is, conjugate base stability. I should write here stability is more, so I should write the stability of conjugate base is more, acidic strength is more. This is the actual reason. Another point is, if I want to find out the equilibrium constant for this reaction, I should write here a reversible arrow, because you all know that no reaction is 100% unidirectional. It has to be a reversible reaction. Okay, everything is not almost completely dissociated, so we are putting this reversible arrow. Now if I want to write the equilibrium constant for this particular reaction, we should write K is equal to concentration of H plus into concentration of A minus divided by concentration of HA. Now since this equilibrium constant is for the ionization of an acid, we denote it by Ka and we call it as ionization constant of an acid. This is called as ionization constant. This particular equilibrium constant only for an acid, since it is the process is ionization of an acid, so this equilibrium constant is called as ionization of an acid. Now we very clearly we can see here the Ka, value of Ka is more, the concentration of H plus is more, and hence the acidic strength is also more. Okay, so this is another definition, another point you can say to determine the acidic strength. Another terminology is here which is called as pKa, and pKa is negative logarithm of Ka. So from this we can say the less the pKa value, the more will be the Ka value and more will be the acidic strength. Okay, so in the book you can see that there are different pKa value is given, and the less is the pKa value, more will be the acidic strength. Okay, but this all finally depends on the stability of the conjugate base. So whenever you talk about any acid strength, the strength of an acid, just look at the conjugate base and see what is the stability factor there, whether there is an stability or not. If there is a stability, then it will be stable. If this is stable, then the ionization will be more and more towards a forward direction, and hence it will release more and more H plus. obviously understand that everything in the nature goes towards stability. So if A minus has some stability factor, then the forward change will be more, and hence the H plus will be coming, the concentration of H plus will be more, and hence your acidic strength will be. So I hope the concept is clear here. Now let's take an example and let me clear your this thing, concepts, okay? So suppose I'm taking HCOOH. Everybody knows this is called as formic acid or methanoic acid, okay? Now, if this gets dissociated, we get HCOO minus, that is formate ion, and H plus ion, H plus. Okay, so we are breaking this bond. I'll show you here, we'll understand this. We will break this bond and we'll write down this. This is called as format ion. Formate ion. Okay, now why this bond is breaking? You can ask me why this hydrogen is not leaving and this hydrogen is leaving. I think there is a reason. This is much more electronegative than this hydrogen. So this will be pulling this bond towards itself, or pulling these electrons towards itself, making, release of H plus ion. So that is the reason whenever any hydrogen is attached to an electronegative atom, suppose this is the most electronegative atom, the hydrogen is attached to this, or hydrogen is attached to a nitrogen atom, say, or the hydrogen is attached to oxygen atom, or it is attached to any electronegative atom, this hydrogen becomes acidic in nature. Okay, and that is why this hydrogen is called as acidic hydrogen, because the electronegative atom will be pulling the electrons towards itself, making the hydrogen release as H plus ion. Okay, understand this. That is the reason that this hydrogen is leaving over here. Okay, now this is a format ion which is a conjugate base over here. This is the conjugate base. So we need to see, and this is the acid. So we need to see if any factor is there which is stabilizing this base. Okay. So we can see that one more thing, remember that a neutral atom is always more stable than an ionized one, or than an ion. It might be anion or cation. If there is a charged ion, I would rather say that neutral atom is more stable than the charged atom. So charged ion, okay. So if there is a charge, the charge has to be dissipated. If the charge is dissipated or distributed, then the atoms gets the stability. If the charge is not delocalized and it is concentrated at one place, then the atom is not stable. Okay. So if we get anything, if we do anything that the charge gets dissipated. Now here we can see that this charge comes here and this bond breaks, and we get another canonical structure here, that is HCO minus double bond O. Okay, and finally you can write down the hybrid structure as HCOO, and this is how, this is delta minus, this is delta minus. So we have this resonating structure over here, one first and second, and that's the hybrid structure. Now if I suppose say I have CH3COOH, this acid now, this is called as ethanoic acid. Let's see the stability, let's compare the stability of ethanoic acid with methanoic acid. So we are dissolving this into water and we are getting the ions at CH3, I'm writing this O here, OO minus and H plus. Okay. Now this is acetate ion. Now we'll see the stability of acetate ion. The stability of acetate ion is less than formate ion. Why? Because there is a factor which is called as plus I effect. This methyl group has a plus I effect, and that is how it is pushing the electrons that side. Okay, so already there is electron density more in oxygen and it is getting more electrons because there is an electron donating group attached to this carbon. You know that inductive effect acts through the sigma bond, and that is how the electron density will be more, because the electrons are pushed towards oxygen and it's more. So the charge is not getting dissipated, rather it is getting concentrated at a particular atom, right? And that is why this makes it unstable. So this is not a very good, stable conjugate base. Though that this will come here and this will come here, you will also get a canonical structure here also. But then this, because of this plus I effect, this will become less stable conjugate base, and that is how we can compare between the acidity of this and this. This is more acidic than this, right? Another thing we can see in, suppose we are talking about phenol. Okay, let's take the example of phenol. So phenol is also more acidic in nature. How it is acidic in nature? Now please do not compare phenol with formic acid and acetic acid, because phenol is another type of compound, formic acid, acetic acid is another type of compound. So we cannot compare the acidity between phenol and acetic acid. Definitely acetic acid will be more acidic in nature, but that depends on pK value again. But I am just telling you the factor here. Okay, so phenol, when dissolved in water, we get O minus, phenoxide ion, and H plus. So this is called as phenoxide ion, and now we are going to see the stability factor of phenoxide ion. Okay, so you can see that this bond comes here and this bond goes like this. So you get another canonical structure where you get double bond O here. This is a negative sign, and you get this structure. Okay, now this bond comes here, this bond goes. So you get another canonical structure, double bond O. These are the two. This is here. This bond comes here. This bond is broken. You get another canonical structure, minus this and this. Finally, this comes here. This is again broken. We get another last canonical structure, that is O minus this, and this. So we get so many canonical structures, and we know that as many canonical structures are there, the compound is that much stable. So the conjugate is, the base is much stable because of this resonance structures, and hence phenol is acidic in nature. Okay, though it comes under alcohol. We have studied this compound in alcohol, phenol and ether, but then still it is acidic in nature because of the conjugate, the stability of the conjugate base. Okay. Another thing is, if there are electronegative electron donating group attached to phenol. Suppose there is an electron donating group here, okay, and there is an electron withdrawing group here. Withdrawing group here, or in the para position only. Suppose I am writing an electron withdrawing group. So it has been found out that the electron donating group, this is electron donating group, decreases the acidity. Okay, whereas the electron withdrawing group increases the acidity. Okay, acidic strength, or you can say acidity. Why that is so? Now let's see what is the reason behind it. I'm taking the example, the first example, phenol. There is electron donating group CH3. Now when you dissolve this into water, the hydrogen ion is liberated and you get the conjugate base, that is this. Okay, and now this is CH3. So now you see that this is electron donating group. So this donates electron, it pushes the electrons inside the ring, and because of that, this here the electron density again increases. Okay, so the charge should get dissipated, as I mentioned to you. It should get dissipated. It should not be concentrated in an area. The density should not increase, but because of the electron density, the electron donating group here, the electrons are pushed inside the ring, and finally it comes to the oxygen. So electron density on oxygen increases. So here we will give the reason that electron density on oxygen atom increases. So we can see that the charge is not getting distributed, but it is getting concentrated at a particular atom, and hence decreasing the stability of conjugate base. Hence acid strength, acidic strength decreases. Okay, so now let me take the example of electron donating group attached to this. So when this is dissolved in water, we get this ion. O minus, and the NO2 is here. I am writing it like this. Okay. Now you can see this bond will come here, and hence this will come here. So if this comes here, this will come here, and finally this will come here. So there will be canonical structures. So the negative charge on oxygen is getting dissipated here. The charge on oxygen gets distributed inside the ring. You can see it's distributed. Hence, stability of this conjugate base increases. Conjugate base increases, and hence the acidic strength increases. Okay, so I hope you understood. This is the concept. So finally, if I give you an example of, say, same type of compound I am giving now. Suppose this is phenol, this is para-methyl, or you can say para-hydroxy-toluene, this is called as toluene. Then suppose we have NO2 group over here, and we have a compound where there are more than one NO2 group. Okay, and suppose we have a compound where there are more than one electron donating group, CH3 and CH3. So we know that electron withdrawing group will increase the acidity, so obviously NO2 group will increase the acidity, and number of NO2 group increases, the acidity still increases. So first, in the first position, this will come OH, NO2 attached here, NO2 attached here. So this will come. In the second position, the compound with one NO2 group will come. So this is in the second position. Now in the third position, only phenol will come, because we know that electron donating group decreases the acidity. So phenol does not have any effect. So phenol will come in the third position. Then obviously number of electron donating group increases, acidity still decreases. So this will be the least acidic in nature. So next will come this one, OH CH3 group here, and the final compound will be more than one CH3 group. OH here, CH3 here, and CH3 here. Understood? So this is the entire concept of strength of acid. So what is our takeout today? The first thing, that is the stability of the conjugate base increases the acidic strength, and not the ease with which the H+ ion released. If the H+ ion is releasing with ease, that means the conjugate base is stable by somehow. So we need to look for the factor which is giving stability to the conjugate base. Another thing is the atom, the simple neutral atom, is more stable than a charged one. And because of that, we need to look for the distribution of the charge. If there is a charge on an atom, how the charge is getting distributed. We need to look for the factors which are helping to get distributed, helping to distribute the charge. So if it is happening, then again the stability of the conjugate base will increase. And another thing we have seen, that if there is electron donating group attached to the benzene ring, then the charge is getting distributed. So the acidity is increasing. How? Because the conjugate base stability is increasing. And if there is a electron withdrawing group, electron withdrawing group is increasing the acidity, and electron donating group, then it is decreasing the acidity. So this is a final takeout of today's lecture. I'll just write it down here. The first point is stability of conjugate base increases, acidic strength increases. Second point is electron donating group decreases the acidity. Number of electron donating group increases, acidity further decreases. Another point is electron withdrawing group increases the acidity. Number of electron withdrawing group increases, the acidity decreases. Acidity increases. number of electron withdrawing group increases, acidity increases. Here number of electron donating group increases, acidity decreases. Yes, number of electron withdrawing group increases, acidity increases. Okay, so this is the entire concept of strength of acid. Thank you so much. If you feel these videos are beneficial to you, please subscribe the channel and press the like button.